Great. Okay, last time we didn't finish the characterizations of invertibility. So we had this theorem that we're in the middle of that said that if A was an n by n matrix, then the following conditions are equivalent to each other. Right? So, and those were one, that A is invertible. Two, that the homogeneous equation AX equals 0 has one and only one solution, like has a unique solution. Has a unique solution, namely the 0 vector. 3, that A could be row reduced to the identity, and 4, that A was a product of elementary matrices. Okay. Okay, and we had proven. So we said that we were going to prove that 1 implies 2, implies 3, implies 4, implies 1, right? And we had done everything except to show that 2 implies 3, right? So we need to prove. We need to show that 2 implies 3. That 2 implies 3. In other words, that if you have one and only one solution, then you're row reducible to the identity matrix. Right? When you do the Gauss-Jordan reduction, you get the identity matrix. Okay. So what we're going to do is we're going to do it by contraposition. We're going to prove the contrapositive. Okay. We're going to do proof by contraposition. So some of you may know that if you have one statement, x implies y, right? X implies y, then that's the same. Logically, that's the same thing as saying that not x implies not y implies not x. Okay, and this you have the statement. And you have the contrapositive statement. Contrapositive statement. Okay. And to prove, if you want to prove the first one, you can prove the second one. You can either of these statements is logically equivalent to the other. So if we want to prove this one, we can just as well prove the other one. Okay. So here we want to prove. We want to show that that this thing has a unique solution, implies that A row reduces to the identity. Okay, and so what we're going to do, we'll prove that if A doesn't row reduce to the identity, if A is not row equivalent to the identity, then AX equals 0 has infinitely many solutions. Okay, and that will be the that's the negation of this. So you have to negate this statement. You have to not logically negate this statement, and you have to logically negate this statement. Okay, right? A row reduces to I. Well, the negation is A doesn't row reduce to I. Right? Is everybody okay? Yeah. Right? If I want to logically negate the statement says A row reduces to I. Well, the negation is A doesn't row reduce to I. Now this one, A has a unique solution. The negation of that would be A doesn't have a unique solution, right? But remember that there are only three possibilities. A has no solution, has one solution, or infinitely many solutions. So the real negation of this is A has no solutions or it has infinitely many solutions. But we know that it's not the case of having no solutions because this is a homogeneous equation. That's impossible, right? So we don't have to worry about that, right? It should be like A has either none, either no solutions or infinitely many solutions. This is maybe more proper, but we don't have to worry about that because it's a homogeneous equation. And so I'm just going to leave it like this. Okay, so that really was the negation, but I'm just making it simpler. Okay. Okay, so let's prove that. Let's prove that if you don't reduce to the identity matrix, then you're going to have infinitely many solutions. Okay. So do Gauss-Jordan reduction on A, and suppose we don't get the identity matrix. We don't get the identity matrix 1, 1, 1, 1, 1. Suppose we don't get the identity matrix. Okay. That would mean that at some point along the way, we don't have a 1 here, right? In other words, first, at some point, at some row, right, the ith, say, the I entry is 0, actually, right? Is 0, right? Because every time you go down in the reduced row echelon form, right? All the pivots are going to move to the right, right? So if it just moves 1 to the right, if it moves 1 to the right, you're going to get the identity. If at every point, if at every step you move 1 step to the right, your pivot is one column to the right, then you've got the identity matrix, right? So if that doesn't happen, that means that you didn't move 1 to the right, so you must have moved 2 to the right, or you must have moved more than 1 to the right, right? That's the only possibility, right? So in that case, at some point you're going to get a 0, right? So you're going to get, maybe you have a 1 here, but then you have a 0, right? You have a 0. Okay. Okay. But in that case, right? In that case, the final row of the reduced row echelon form is all zeros. Right? The final row will be all zeros, but then you've got an underdetermined homogeneous system. Right? So you have an underdetermined homogeneous system. Right? Which means you have infinitely many solutions. So you have infinitely many solutions, and so you're done. Right? We see that if you don't get the identity matrix, you end up with infinitely many solutions. Right? If you're not row reducible to the identity, then you end up with that AX equals 0 has infinitely many solutions. Okay, so this is, yeah, Mariah.
So how do you know the final row is all 0?
Well, because you know that the leading entry in the reduced row echelon form, the leading entry is always 1 to the right of the row above, right? But if at some point you step two over, then that last entry doesn't have anywhere to go, right? You see, like, if I'm in a 3 by 3 matrix and I step 2 over early, well, my leading entry has to be to the right of the one above, right? And that's, if I'm a 4x4, right? Suppose that I step 1 over at some point. I step 1 step too far. Well, my leading entry has to be 1 over, but I'm gonna have stepped more than n. I'm gonna have reached the final column before I reach that final row, right? And so the last row will have no entries. We'll have no we'll have no non-zero entries. Does that make sense? Sort of. Okay. So this is maybe the this is maybe the I don't know. I wouldn't call this sophisticated, but if you're confused by this, that's okay. Ask questions. Anybody confused by this? Okay. So right, we're saying that that if you're non-equivalent to the identity matrix, then you've got infinitely many solutions. And what we see is that if you're non-equivalent to the identity matrix, you end up with a zeros. The last row is going to be all zeros. Right? But that means you've got an underdetermined homogeneous system, and so you've got infinitely many solutions. Okay, yeah, Joel.
I'm still confused as to why you get the last row all zeros.
Well, so remember how the reduced row echelon form works. Every row, the leading entry is going to be 1 to the right, at least 1 to the right of the previous row. Okay. Now, if at some point, so here's the identity matrix, right? Looks something like this. Everybody stepped. Whenever we went down a row, the leading entry was exactly 1 to the right. Okay. Now suppose at some point you step 2 to the right. You step more than 1 to the right. Well then, these guys have to shift over, right? But then there's no space for the last guy, so it becomes all zeros.
But how do you know that there will be like an entry that has a 0 in like you said, in the ith row, the I entry will be 0.
Yeah, so that's, how do you know that's going to happen?
Yeah.
So if it doesn't happen, that means that the ith entry is 1. But then if the ith entry is 1 for every row, then you've got the identity matrix, right? We're assuming that you don't get the identity matrix.
Oh, so just by like assumption.
Yeah, you say, suppose we don't get the identity, suppose this doesn't result in the identity matrix. The only way that can happen is that there's got to be a 0 in one of the diagonal entries.
Okay. But
But then that makes the last row zeros, and then so you've got infinitely many solutions. Okay. Okay, so that's the last bit. That gives us 2 implies 3, and so we see that all these things are the same. Okay, so all these things are the same. That invertibility is the same thing as being row reducible to the identity, et cetera, et cetera. So, okay. Okay, is everybody all right? Any questions? Any questions? Okay, if it's not completely clear, that's okay. I think most people don't necessarily understand everything right when they see it. I never understood anything in my linear algebra class when I took it. I'd always go back and recopy everything that I'd written down, and then think about it for a few hours, and then maybe it would start to make a little bit of sense. So don't worry, that's all right. If you're confused, that's okay. It just requires some more thought. Okay. Okay. So we're going to use this theorem to calculate inverses. Okay. So this theorem gives us a way of actually calculating an inverse, and it's based on the following observation. So observe, right? Say A is invertible, then A can be row reduced to the identity matrix, right? That means that there are elementary matrices E1, E2, E3, En, right? I.e. there exist elementary matrices such that a hit with these elementary matrices is the identity matrix. Right? That's what being row reducible to I means. Right? But then, if you do that, you see what the inverse is. What's the inverse of A? The inverse of A is this thing right here. Right? In that case, En through E1 is an inverse. Right? Because you have this guy times A is the identity. Right? Okay. So to calculate A inverse, what you do is you take A, the matrix A, and you put it next to the identity matrix. Okay? And then you apply Gauss-Jordan reduction to A. But do the same operation to I should say, while doing the same operations to I. Right? So you say, okay, I'm going to do something to A. I'm also going to do that something to I. Right? I'm going to do another thing to A. I'm going to do the same thing to I. Right? Eventually, you come to down to I. I'm sorry, you come down and you reach I. Okay. You finish your Gauss-Jordan reduction, and if your matrix was invertible, then you get I. Right? And when you stop there, you say, and then you stop. And you say, okay, look at the right side, that's A inverse. Right? A inverse, you record it on the right side. Right? When you get I, this thing over here, this right-hand side is the inverse. And if you don't get I, then you know you're not invertible. Okay. So this theorem, basically gives us a method. This theorem basically gives us a method. Okay. So yes.
What is RHS?
The right-hand side. Sorry, the right-hand side. The right-hand side is A inverse. Okay. Is everybody okay? There. Okay. Okay, so let's do an example of this. 1, 3, -2, 2, 5, -3, -3, 2, -4. Okay. Take a minute or two and see if you can make some headway on finding the inverse. Okay. What would you do to get the inverse? Okay, let's not spend too much time on this. It's not the most interesting thing. What would you do? What would you do? How about you, Tara? What's the first thing you're going to do?
Reduce the left-hand side.
So what's the first row operation that you would use to change this thing into the identity matrix? Right. You're going to do Gauss-Jordan reduction. So that involves getting a pivot here. Well, we already have a pivot here. Then you use the pivot to clear out the elements below and above. They're on above, so we clear out the guys below.
Yeah.
Right. So we're going to say, okay, take row 2 and change it to row 2 minus 2 row 1. Right? So you get 1, 3, negative 2, 1, 0, 0. This minus twice that is 0. This minus twice that is negative 1. This minus twice that is 1. This minus twice that is negative 2. 1, 0. Right? 3, 2, negative 4, 0, 0. Right? Then we're going to use this guy to clear out that guy, right? Clear out the negative 3. So row 3 becomes row 3 plus 3 row 1s. Right? So we get row 3 negative 2, 1, 0, 0, 0, negative 1, 1, negative 2, 1, 0. We get 0. We add 3 to that. It's 11. We get 3 to that. We get negative 10. 3 to that. 3, 0, 1. Right. Then we use this guy to clear out above and below. So we say, okay, row 1 turns into row 1 plus 3 row 2s. Right? 1, 0, 1, negative 5, 3, 0. 0, negative 1, 1, negative 2, 1, 0. 0, 11, negative 10, 3, 0, 1. We use this guy to clear out that guy, right? So row 3 becomes row 3 plus 11 row 2s. 1, 0, 1, negative 5, 3, 0, 0, negative 1, 1, negative 2, 1, 0, 0, 0, 11 of those guys is 1, negative 22, negative 19, 11, maybe then we multiply row 2 by negative 1. Right? We end up with 1, 0, 1, negative 5, 3, 0, 0, 1, negative 1, 2, negative 1, 0, 0, 0, 1, negative 19, 11, 1. And then we use this guy to clear out above, right? So take row 1 and subtract off row 3 from it. Right? So we get 1, 0, 0. We get 14, negative 8, negative 1. So 1, negative 1, 2, negative 1, 0, 0, 1, negative 19, negative 1. And the last one, we say, okay, take row 2 and add on row 3 to it. And we get 0, 0, 14, negative 8, negative 1, 0, 1, 0. We add on row 3 to it, so we get negative 17, 10, 1, 0, 0, 1, negative 19, 11. Don't worry about copying this all down, right? It's not that important. Right? Just understand the procedure. Right? The procedure is you do Gauss-Jordan reduction on the left-hand side, and whatever you do to the left-hand side, you do to the right-hand side. Reduce all the way down to the identity, and whatever's on the right-hand side is your inverse matrix. So this thing is the inverse Right? If this was A, we call this thing A, and this thing over here is A inverse. Okay. I think the main thing to understand is just what we said before, that how this procedure actually works. Right? It works because of the theorem. Right? The theorem says that if you're invertible, that means that you're row reducible to the identity. Right? And you know that in that case, the inverse matrix is whatever you did, right, is that product of elementary matrices. Anybody have questions? Okay. Yeah, Ethan.
Sorry, so the separating of row 1 is row 1 minus row 3.
Yeah.
I'm not sure. So I'm just subtracting 1 from 0. Why does the row get reduced to 1, 0, 0?
Because I take row 1 and I subtract row 3 off from it. So I get 1, 0, 0, 14, negative 8, negative 1. Right? I take row 1
I'm sorry, yeah.
and I add on negative row 3 to it.
Yeah, I was thinking about row 2.
Okay. Tara, do you have a question? Do you want me to answer it? Or?
Well, no, I was just clarifying, like, so you're just trying to make the left side the identity matrix, and then whatever comes out on the left side after you make the right side the identity matrix is the inverse. Is that what the process was?
Yeah, whatever comes out on the right side after you make the left side the identity is going to be your inverse.
Okay.
Unless you don't actually, if you don't get to the identity here, then your matrix was not invertible.
Okay.
Right, so. Okay. Okay. So the other class, at this point I did a problem. This problem sort of led us far afield. Let's take 1 minute on a problem. Okay, so here's a problem. Suppose that A is a 4x4 matrix, and that A1 plus A2 equals A3 minus 2A4. Okay. That you have some relation between the columns, right? The first column plus the second column equals the third column minus twice the fourth column. Show that A is not invertible. And the hint is, this is directly related to the theorem that we proved at the beginning. The theorem, remember, A invertible is the same thing as AX equals 0 as one solution. The same thing as A being more equivalent to identity is the same thing as A equaling the product of elementary matrices. Tara.
Because A1 plus A2 equals A3 minus
2A4.
2.
Yeah. Yeah.
But do we
Yes.
have like a fake, is that a row, is that a column vector?
These are column vectors, yeah.
Oh, okay.
So these are column vectors. So suppose you have a 4x4 matrix and the columns have this relation. The first column plus the second column, or to make it maybe clearer, that if I look at the first column, negative the first column minus the second column plus the third minus twice the fourth, I get the 0 vector. I get a 0. Why would that mean that your matrix is not invertible? Why does that tell you that your matrix is not invertible? Anyone see it? If you don't, I'm just going to leave it. I don't want to get into it, given what happened in the first class. Harrison.
I was just wondering what the question was again.
The question is, show that if this happens, then your matrix can't be invertible. Your matrix is non-invertible. Show that if the columns of your matrix satisfy this relation, then your matrix cannot be invertible. Lorraine.
Oh, well, no, maybe. Okay, this is wrong now. I was just gonna say, doesn't that mean that one of the rows would then be 0?
No, right? You know that the sum of the columns is going to be 0. So?
If the whole, like, all the columns equal 0, and like the AX also equals 0, that means all those columns have to equal AX. Is that, but then, like,
No. I mean, so, I mean, this is, so you're saying,
because there's like a certain format that the columns go in when they like are set equal to AX, and that's not the right format. Does that make sense? So like, you,
yeah, so it's related to this, statement. But I think let's stop here, and I'll just leave it as a homework problem. Yeah.
Does it say that the matrix is undivided?
If the matrix is what?
Undivided.
Under determinant?
Oh, yeah.
Under determinant? Let me just leave it there. Yeah. So, yeah. Okay, yeah,
That was a teaser.
yeah, it was a teaser. Okay, maybe I'll just put it on the homework. Okay, because I want to get into the next section, the notion of the determinant. So this is a pretty important notion, the determinant of a matrix, the determinant of a matrix. This is not exactly what it is, but it's sort of like this. You take a matrix, and then you get some number out of it. Okay, and that number tells you if the matrix is invertible or not. Okay, so you have this matrix, you do some procedure, and you get a number out of it, and that number will basically say invertible or non-invertible. It will give you information. If the number is 0, it's not invertible. If it's not 0, it is invertible. Okay, so that's one thing that the determinant tells you, but that's not all actually. There's more than that. Okay, so we need to construct this number. The construction is kind of complicated because it's a recursive construction. Okay, so we'll do it like this. Okay, so so let's start like this. Definition for 1x1 matrices. The determinant of the matrix is defined to be that entry. Okay. If the matrix consists of one number, then its determinant is that one number. Okay. Right. If your matrix is the number 5, then the determinant is just that thing. Now we need to introduce something funny called the minor matrix. So minor matrix. So given an n by n matrix A, we define the ij minor, mij, as the n minus 1 by n minus 1 matrix, the square but smaller matrix obtained by removing A's ith row and jth column. Okay, so you take your old matrix, you cut out one row and you cut out one column. That thing is called a minor matrix. Yeah, Connor.
What's between the n minus 1s?
That's a times. So the n minus 1 by n minus 1. Okay. So, for example, if A is 1, 2, 3, 4, 5, 6, 7, 8, 9, then if I say M11, that means you eliminate the first row and the first column, right? And so you end up with 5, 6, 8, 9. Okay. If I say M22, you eliminate the second row and the second column. So you'd have 1, 3, 7, 9. Right? M22 means you eliminate the second row and the second column, and you get 1, 3, 7, 9. Okay. Everybody all right? Nothing difficult so far, right? You have a matrix, you chop off you throw out one row and one column of it. That thing's called a minor matrix for the original. Okay. Third definition, the ijth cofactor of A, the ijth cofactor of A, which we denote Aij, is defined as -1 to the I plus j times the determinant of the minor matrix Ij, of the Ij minor matrix. Let me do one more thing and then I'll give an example. Okay. So no, actually, let me give an example right now. Okay. So suppose we have this matrix 3, 2, -2, 4. Okay. So A is this. Then if I say A11, the 1, 1 cofactor, what does that mean? That means you take -1 to the 1 plus 1, and you multiply that by the determinant of the 1, 1 minor. Okay, the determinant of the 1, 1 minor, well, the 1, 1 minor is what you get when you cross out the first row and the first column, right? So that's the determinant of the number 4. So that's just 4. Okay, so you get -1 squared times 4. So the cofactor, the 1, 1 cofactor is 4. Yeah, that's right.
So when trying to find the determinant, basically our goal is to reduce the matrix to a single number?
Yeah. Okay, and so now we can actually make the definition of the determinant now that we have all the pieces. The determinant, so if A is an n by n matrix where n is bigger than or equal to 2, then the determinant of A is defined to be, actually let me go over here. A an n by n matrix where n is bigger than or equal to 2, then the determinant of A is defined like this, and it's kind of a funny definition. What you do is you take the 1, 1 entry and you multiply by the 1, 1 cofactor. And then you add on the 1, 2 entry times the 1, 2 cofactor. Blah, 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 the 1 n entry times the 1 n cofactor. So it's a dot product, actually. The dot product of the first row against the first row of cofactors. Okay, it's a dot product. Yeah, comments?
What's a cofactor?
Cofactor is this thing over here. The ij cofactor is -1 to the I plus j times the determinant of the ij minor matrix. Okay, we'll do an example. We'll do an example in a second. So, okay. So, okay, so notice, so for example, if we take the determinant of that thing we just had, 3, 2, negative 2, 4, well, that's going to be A11 cofactor A11 plus A12 cofactor A12. Okay, what's that? A11 is 3. The 1, 1 cofactor is negative 1 to the 1 plus 1 times the determinant of the 1, 1 minor matrix. Right? Well, the 1, 1 minor matrix is the matrix with the number 4. Everybody see that? Just take a look, right? Right? A11 is 3. A11 is 3. Cofactor A11 is negative 1 to the 1 plus 1 times the determinant of the minor that you get by crossing off the 1, 1. Right? So you get 4. Okay. Okay. Then here you get A12, that's 2, times negative 1 to the 1 plus 2 times the determinant of the 1, 2 minor matrix. Well, when you cross off the first row and the second column, you get this negative 2. You get this negative 2, right? Okay. So what do you get? You get 3 times 4 plus, so minus 2 times negative 2. Right? In other words, you get 16. So the determinant of this guy is 16. About.
If we had a 3 by 3 meters, that means we basically have like 3 summations. We add 3, and if you have a 4 by 4 matrix, then you have 3 by 3.
Yes, what you're saying is the awful, what's awful about this. Okay, so what you're saying is the recursive structure of the definition, right? That the determinant of a matrix is defined in terms of determinants of smaller matrices. Those are in turn defined in terms of determinants of smaller matrices, in turn smaller matrices down to the 1 by 1s which we have. Okay. Okay, so for example, if we're asked to find the determinant of 1, 0, 7, 1, 3, 2, 1, negative 2, 4, well, that's going to be the determinant of, that's going to be 1, negative 1 to the 1 plus 1 times the determinant of, you need to cross 3, 2, negative 2, 4. 3, 2, negative 2, 4, plus 0, well, we don't really have to write this out, 1 plus 2 times the determinant of 1, 2, 1, 4, plus 7 times negative 1 to the 1 plus 3 times the determinant of what?
1, 3, 1 minus 2.
1, 3, 1 minus 2. 1, 3, 1 minus 2. Okay. And if you look at the determinant of a 2 by 2, you see that it turns out to be AD minus BC. Okay, so that simplifies things a little bit for us, right? We get 1 times 12 minus, we get 16 plus 0 plus 7 times negative 2 minus 3 is negative 5, so we get negative 19. Yeah, come on.
Where did 16 come from?
The 16 comes from here, right? We've got 1 times negative 1 squared, that's just 1, right? So we get 1 times the determinant of this. The determinant of this is AD minus BC, so 3 times 4 minus 4, so 12 plus 4 is 16. Okay, so you see that if we asked you to do a 4 by 4, it would be even more awful right? Because you have to take these guys and multiply by determinants of the 3 by 3s. The determinants of the 3 by 3s, you would have to calculate determinants by 2 by 2s, and so on and so forth. Right, so it's pretty awkward. Okay. Let me just say one thing that's a cool thing, which is that, so notice, the determinant of A is defined as this 1, 1, A11 plus A12, capital A12, whoops, A12 plus A1n, capital A1n, right?
I actually have a question about the earlier. How'd you get -5?
Because you get -2 minus 3, right?
Okay.
So the determinant of 2 by 2, when you work out the formula, it turns out to be AD minus BC. So back here, so here's the punchline. Sorry to keep you over. The determinant is defined like this: A11 cofactor A11, A12 cofactor A12. Blah, blah, blah. There's something that's a little bit strange about that. What's strange? It's the first row. Why the first row? Why don't we say it's the second row, like A21, capital A21, A22, capital A22, A2n, capital A2n, right? Or why don't we say that we use the first column, right? A11, capital A11, A21, A21, capital AN1, whoops. Right, why don't we do something like that? Hold on. Sorry. And the punchline is that all these numbers are going to be the same. Okay, so no matter, so there's a theorem that says that no matter what row or column you expand down, the result is the same. Okay. Now we're not going to prove this theorem because it's kind of intricate. Okay. If you want, I can give you a reference. There's a book called Linear Algebra by Frawley and Beauregard that has it, but it's not that interesting a proof. But the use of it is that if you had some sort of gigantic matrix and you notice that, say, the 16th column happened to be all zeros, then you could say, okay, I know that the determinant is 0, right? Because I'm going to do my expansion down that column, and then I just be multiplying all my coefficients here would be 0, right? And so you can look at your matrix and choose the most convenient row or column to find the determinant down. Okay, I'm sorry to keep you over. That's it for today.